Hi, I'm Jimmy, aka Perceptes. In this video, we'll be diving deep into Walk 4, a quad brownian accumulator Eurorack module from Joranalogue Audio Design. Don't let the description scare you. Walk 4 isn't too hard to understand, and once you understand it, you'll find lots of uses for it in your patches, from a sound source to a sequencer. This video consists of an overview of Walk 4's features and user interface, followed by examples of the patches suggested by Joranalogue in the Walk 4 user manual, plus a few additional patch examples. We'll start with some clips of the patches to come. If you like what you hear, stick around for the details. Let's start with an overview of the module to explain its feature set and user interface. As it says on the panel, Walk 4 is a quad brownian accumulator, which is a bit of a mouthful, but we can break it down. Quad obviously means 4, because there are 4 identical channels on Walk 4. Brownian refers to the idea of Brownian motion, which is the observed behavior of a particle floating in a liquid, the way it sort of meanders around, and it eventually will go from point A to point B, but it doesn't take the most efficient path to get there. You can kind of liken this to a person who's walking down the street drunk, the way they kind of stumble and trip over themselves, but eventually get where they're going. And so a Brownian walk is also sometimes called like a drunken walk. An accumulator is a circuit that holds on to and remembers a voltage, and then you can add or subtract from that voltage to build it up or decrease it over time. Walk 4 has 4 accumulators, and those 4 accumulator outputs are available at the bottom with these 4 LEDs. The strength of the LED is the strength of the voltage coming out of that jack. There's also a built-in clock in Walk 4 that's available via this clock out jack and is normaled to these trigger inputs, which we'll explain in a minute. The speed of the clock is determined by the rate knob and the audio versus low position switch. This allows it to work at both audio and modulation rates. When it's in the low mode, turning the rate knob all the way counterclockwise will bring it down to a period of about 3 minutes, which is 5.5 millihertz, and bringing it all the way up to the top will be 180 hertz. In the audio rate mode, the lowest value of the rate knob will be 22 hertz, while the highest will be 22 kilohertz. So at this rate, you can actually use the outputs of the accumulators as an audio rate oscillator. As I mentioned, the clock is normaled to the trigger inputs for each of the 4 accumulator channels, and this is what causes the increment of the accumulator. So on each clock pulse, a value is taken and added to the current sum of that accumulator. So it's sort of like a sample and hold, but it's not starting from scratch every time. It's adding to the previous value so that it continues to build and build and build. The amount that's added on a trigger input is determined by a number of sources. The first one is trend. So if I bring trend all the way down, we'll see that the trace on data, which is the output of the first accumulator, just stays flat because we're not adding any voltage to it. It just stays where it is. Trend will give a fixed offset between 0 and 5 volts. And so the higher that you increase this control, the larger the step between each trigger will be because it's adding more voltage per step. So going all the way up, we have fewer steps because each one is larger. Now the reason that it's actually resetting and going back down to 0 is because of this auto reset switch, which I've had enabled this entire time. In auto reset mode, when the value on an accumulator reaches 10 volts, which is that top point, it will automatically reset to the bottom at 0 volts. If we turn this off, then the voltage will stay saturated at 10 volts when it reaches that point, and the only way to get it to go back down is to send a trigger to the reset input, or to use some different features, which we'll see in a minute. Most often, you'll probably want the auto reset on, so that you have sort of a cyclical staircase waveform that continues forever. The second factor determining the increment on a given step is the volatility control. This is backed by 4 independent noise sources inside WAC4, one for each channel. And this is more like a sample and hold, where it's sampling a random value from the internal noise circuit on each step, and that value can be either positive or negative. It will then sum this with whatever fixed voltage you've set via trend, and as you turn this up, you'll start to get more drunken walks, hence the Brownian motion we described earlier. You can see that the step sizes kind of vary. Sometimes they're bigger, sometimes they're smaller. And at really high values and with lower trend, we may actually see the signal go negative. Occasionally you'll see the LEDs go blue. That indicates a negative voltage. So introducing voltage from volatility, which is negative, may cause the staircase to go down as opposed to up, which it otherwise would always do, because trend is always positive. The third factor that influences the amount that an accumulator is incremented on a given clock pulse is the value inputs, and there's one for each of the 4 accumulators. This allows you to send in a voltage from an external source, and whatever voltage is present on the value input at the time that the clock pulses, that value will be added to whatever trend value you've set, and whatever value has been sampled from the internal noise source due to the volatility settings. This last knob, constrain, is maybe a little bit harder to explain. It's sort of like a compressor in that it prevents the signal from getting to its saturation point at 10 volts too quickly. And it does that with a negative feedback loop where it's sending some amount of the accumulator's output back into its input. As you start to bring the constrain knob down, it's going to be sort of pushing down on that top voltage. And if I bring it to about, 1 or 2 o'clock here, you should be able to see on data that the step sizes when they're near 0 volts are much larger than they are when they're near 10 volts. There's a really good description of this behavior in the manual for WAC4, which kind of describes it as a spring. If you imagine that 10 volt point is like a spring that's anchored to a wall, and the voltage is starting to push in against the spring, the closer it gets to the wall and the more the spring is pushed in, the more resistance there is and the harder the spring pushes back against that signal. And that's essentially what we're seeing happening here. If you go really low on constrain, really pull it in, then the negative feedback will actually cause decrement to the value. So you can sort of see it's trending down slightly, especially if I turn up the rate. So I can increase the trend to make it go up, and then if I bring the trend down, theoretically it should stay flat, but it actually goes back down because that negative feedback loop from the extreme constraint is bringing it down. So we'll see in the patch examples some ways that this can be used, but it's very useful for when you're using this for like a pitch sequence, for example, keeping the values in kind of a narrower band so that you don't go to extremely high pitches, which may not sound very musical. There's another way to change the output of the accumulators, and that's this add input at the bottom left corner. This is different than trend, volatility, and the value inputs because it doesn't change the increment value on each trigger. What it does is it sums any voltage coming in on that jack with the outputs after the increment has already happened. And it applies to all 4 outputs in the exact same way at the same time. So an example use case for this would be to transpose pitch sequences. If you have 4 different pitch sequences coming out of the 4 accumulators, you could send an offset voltage on a downbeat of a measure, for example, to change it to a different baseline pitch so that the relative distances between the pitches stay the same, but they start from a different point. Finally, the trigger inputs allow us to decouple the accumulators from each other in terms of when they change to the next value. So far, we've just been looking at traces where the clock input is normaling into these 4 triggers, and so they're all happening at the same time, and we've just been looking at the trace of one of them to explain how it works. But now I'm going to turn on the second output. The green and the blue traces are just layered on top of each other, so you can't see the blue one right now. I've got Pamela's Pro Workout set at 150 BPM. The first output is just once per beat. And the second output is 4 times per beat. So if I plug those into the first and second trigger inputs respectively, bring the trend up a little bit, then we'll see that the 2 accumulators are now progressing at different rates. It might be useful if we listen to some audio for this. So let me unmute the Nano Module's ONA. I have the audio of the square wave plugged into the mixer, and we're sending that green trace into the volt per octave for changing the pitch, and we're sending the blue trace into the pulse width modulation for changing the width of the square wave's pulse. So you should be hearing that the pitch is changing less often than the timbre of the square wave, which is changing multiple times per value of the pitch. Because Walk 4's clock can run at audio rate, we can use the 4 accumulators as 4 oscillators. The staircase waveform that they create will essentially be the wave shape of the oscillator. Here, we're going to be using mimetic digitalis, which is a 4-channel CV sequencer, to send 4 different voltages into the 4 different value inputs, respectively. We're not going to be using the sequencing aspect of this, we're just using it on its first step to send 4 different voltages. Right now, with the trend knob and the volatility knob all the way down, and the 4 channels just sending out 0 volts into the value input, we're not getting a staircase waveform, and so all we hear is a crackle due to the analog circuit. The 4 outputs are going into a mixer, and then back into a low-pass filter, and back into the mixer again for some effects that we'll hear later. We'll talk about the envelope in a bit. So right now I have all 4 channels on mimetic digitalis selected, and so as I turn the knob, it's going to increase the voltage that's being sent out of all 4 of them by the same amount, and that will start to increase the increment of the accumulator, and we'll start to hear a pitch. So there's our 4 waveforms, all operating at the same rate, and at the same step size, because we're sending them the same voltage on each clock input. Because they're operating at the same rate and they have the same waveform, you can see that there's going to be a little bit of phase cancellation. So changing the relative volumes of each one in the mixer will also change what you hear, and turning up the amplitude of one of them might actually make the sound quieter. What we're going to do is increase the voltage for these separately. So I'm going to deselect the 4th channel so that when I turn the knob, it'll only affect the first 3 accumulators, and we're going to increase the value again. And let's deselect the 3rd channel and do that again. And deselect the 2nd channel and again. There we go. Now we've got essentially a chord, because we've changed the cycle of the waveform for each of the channels. A notable thing about the relationship between the 4 waveforms is that they're integer divisions of each other. Every time you increase the increment amount, it gets to the 10 volt point sooner and resets back to 0. And in effect, that's why the pitch is higher, is because we've got a faster frequency because the reset is happening sooner. But those are integer divisions of each other, because there can only be so many staircase steps before it resets. And so this is actually in just intonation, which is an alternate tuning form from what we usually use, where all of the pitches in sort of the piano keyboard scale are exactly equidistant from each other. This will give you slightly different relationships between intervals. The volatility control at audio rate will introduce some of the noise into the signal. Let's listen to that and take a look at how it affects the waveforms. So we can sort of crossfade from a chord to essentially pure noise and back. I've got a trigger sequence coming into the quadrat, and we're going to use that envelope generated by that for the FM input of our filter to create a little pattern out of this chord. And we're going to use a copy of the trigger for the 2nd envelope, and we're going to send that into the volatility input, which will give us a little burst of noise right on the attack of each beat. You hear that burst of noise right at the beginning, so we can use a controlled amount of volatility to enhance the attack of each of our notes. And the decay time affects how much of it you hear before it fades away. At audio rate, the rate CV input will track volt per octave, so I'm going to send a pitch sequence into it, get a drum and some effects going. So you can sequence the chords, sort of move them around, but the relationship between them stays the same. And we can always change the intervals by changing the value inputs. So we can get combinations that are maybe a little more harmonic, ones that are a little more inharmonic. Like this. And we can also play with the trend to add a static step size to each clock pulse. And this can give you some really wild demonic sounds. At lower clock rates, or with an external clock patched into the trigger inputs, Walk 4 is really good at generating pitch sequences, or even deriving one from an existing pitch sequence. In this patch, I'm using Pamela's Pro Workout to send 4 unquantized voltages out in a loop. And that's the bass sound that we're hearing. That's going through the green trace on data and then into the barred quartet for quantization, controlling the caster side of Castor and Pollux, a dual oscillator. And I've just got an envelope and a VCA off screen that's kind of giving it that steady pulse on the quarter note. I've then taken a multiple of the voltage from Pamela's Pro Workout pre-quantization and patched that into the value input of the first accumulator. We then have a clock signal that's going at 4 times the clock rate, so that's every 16th note, and it's triggering the first accumulator at that rate. Let's bring that in again and listen to the sound of that second oscillator, which is the Pollux side of Castor and Pollux. So remember, because Walk 4 is an accumulator and not a sample and hold, every time that 16th note pulse triggers the accumulator, it's going to add the current value from that green trace to the existing value of the blue trace. And hence, even with volatility and trend all the way at 0, we're creating our usual staircase waveform by adding new values on every pulse and creating this arpeggio. And that's derived from the values of our bass sequence. Of course, we can change the controls on Walk 4 to modify the melody. If we add some trend, then those steps become larger and you get fewer notes before you hit 10 volts or the reset input to start your sequence over. In this case, I'm sending a reset from Pamela's Pro Workout at a divide by 2 clock. But we could unpatch that, and with auto reset off, we'll just stay at the top pitch forever. We turn auto reset on. Then the loop point will be different based on the step sizes. Introducing a little volatility will vary the sequence each time it loops through, because the step sizes won't always be the same. In fact, they might even go negative. Let's patch that reset back in. You notice that we're ending up with a lot of very high voltages as we stop on that peak value. We can use the constrain here to make that less likely, or stay in lower ranges. Especially with the trend and volatility down. So now with the constrain brought down, the rate of increment is lower, and it doesn't get to that very high pitch before it gets reset by the divide by 2 clock from Pam. So every time you change any of these knobs, you'll vary the sequence. And because they're both quantized to the same scale, it'll sound great with the original sequence that it's being derived from. We saw previously that at audio rates, with the volatility turned up, Walk4's accumulators become a source of noise. Noise is a classic building block in synthesis, used for adding some texture to melodic sounds, or especially for percussion. And that's what we're going to do here. I've got Pamela's Pro Workout serving as a sequencer for some rhythmic sounds, and I've got a kick drum and a snare drum configured off-screen with the first 3 channels. And then we've got 2 channels that are going to be controlling an envelope that's coming into a VCA, and we've got the 2 noise sources from the first 2 accumulators of Walk4 running through data, which is what we're looking at, through the 2 sides of blades, which is a dual filter, and then into the VCA, which is going to be triggered by the envelopes. But let's just listen to the sound of the noise first before we start using it for percussion. So I've got the first accumulator panned slightly to the left, and the second accumulator panned slightly to the right, so that we can kind of hear the difference. And they're a little bit different than sort of a classic white noise sound because it's not generated entirely by just random voltages. It's, of course, a random noise source added to the accumulation. So you get this kind of nice sort of hollow wind-like noise sound. And of course, the quality of the noise can be affected by the controls on Walk4. So bringing down the volatility will sort of decrease the amplitude as we start to get away from the randomness that generates the noise sound. And similarly, bringing down the constraint will also change the quality of the noise. Sort of like a low-pass filter almost. And trend will also affect the sound. You can see that it starts to go primarily into the upper voltage ranges and you get more of a high-pass filter sound. But we can start our clock and start applying those envelopes to the control voltage of the VCA. We get little bursts of noise. When combined with a kick and snare, can give you a pretty cool beat. And of course, passing through a filter gives you additional options for sound design. For these kind of hi-hat-like percussive effects, usually a bandpass filter is a good idea. So let's go into bandpass mode on each channel. Turn up the resonance for some additional amplitude around the cutoff. And then we'll move the cutoff frequency of the 2 noise sources into 2 different positions. And you start to get a really cool sound, especially with a little delay and reverb on it. It sounds great. You can really hear the resonant pitch in that percussive sound. And of course, we've still got 2 outputs remaining on Walk4, 2 additional accumulators that we haven't used. So we could always patch those into the filter to modulate the cutoff of each side. Just bringing in the value just a little bit, and we get a little bit of frequency modulation on that resonant filter cutoff for some additional sound. And then, because we can change the quality of the sound by changing the controls on Walk4, we can also take some additional modulation, in this case from Pamela's Pro Workout, and we can plug those into the controls on Walk4. So I'm sending a random slewed voltage into constrain and into volatility, which just gives a little bit more of the kind of unpredictable, chaotic nature of the sound. One of the great things about modular is that when you have a control voltage, you can send it to any destination in your system. And there's so many different possibilities for sounds that you can create with modulation. As a source of 4 different voltage signals, Walk4 is excellent as a source of modulation to send to various destinations. In this patch, I'm using all 4 of the accumulator outputs and sending them to different timbral modulation points across my oscillators. The drone that we're hearing is coming from Mutable Instruments plates in chord mode, and then running through beads for some texture and grains. The plucky voice is coming from Vert Iter Legio, the noise engineering oscillator. And we're sending the accumulator voltages into different parameters. So the first one is going into an attenuator off screen, and then coming back into the low-pass filter of dual dagger, which is low-pass filtering vert interlegio with some resonance turned up. The second accumulator is going into plates' timbre, and I'll now turn up the signal on that, let some of it through by increasing the value on this internal attenuator. And this will change the inversion of the chord that plates is playing. The third accumulator's output is going to the morph control on plates, which changes the waveform of the chord. So we'll bring in a little bit of that too, not too much. And then our fourth accumulator is being copied to two destinations. One is the time control on beads, which changes where in the recording buffer the grains are drawn from. So let some of that signal through. And then an attenuated copy is going into the tang input on vert interlegio, which will provide some timbral changes. With a little bit of delay and reverb, we can get some really beautiful effects from this modulation. Right now I'm just using a very slow stepped waveform on each of the Walk 4 accumulators, but we can start introducing some volatility, maybe change the rate to get a more unpredictable pattern that seems to jump around a bit. And with a fast clock that's desynced from the clock that's triggering our plucky voice, we can get some pretty wild and unpredictable effects. This last patch is kind of a combination of ideas that we've explored already. We're using Walk 4's accumulators to sequence pitch across 4 different oscillators. And we're using a slowly advancing sequence on mimetic digitalis to send a voltage into the add input to offset all 4 accumulators every 4 measures. The accumulator output is going into the quad VCA before it goes into the barred quartet for quantization, and that means that we can modulate the amount of signal that gets sent to the quantizer, and hence changing the amount going through will change the sequence. I've got some slow modulation signals patched into the CV inputs of the quad VCA. And now I'll bring those up. One for each voice. So now the speed of the modulation will determine the rate at which our pitch sequences change. Right now, all of the voices are synced in terms of when they change pitch. But if we introduce some volatility, then the randomness will be different for each of the accumulators. And with the auto reset on, they'll reset down to the bottom pitch at different times. And so we'll get this kind of desynced, constantly changing rhythm and melody. With higher volatility, we'll start to get some downward motion as well, especially if we turn down the trend a little bit. And of course, we can use constrain to focus the pitches in the lower range. This is a way you can get some really beautiful sequences across multiple voices to create interesting and pleasant harmonies. I hope you enjoyed this deep dive into Walk 4, and I hope it gave you some ideas for how to use it in fun and interesting ways. If you found the video valuable, I hope you'll follow along for more like it. I'd also very much appreciate your support on Patreon. You can join for free, or chip in a few dollars a month for step-by-step patch notes for videos like this one, high-quality audio downloads of every musical performance posted to the channel, sample packs, full access to Discord, and more. Check the video description for details. If you want to get Walk 4 for yourself, you can also support my work by ordering one from Perfect Circuit using the link in the video description or the pinned comment. This will earn a small commission for me at no additional cost to you. Thanks so much for watching. See you next time.